All right, so we're on example 8. Example 8 is going to be somewhat a review because we've done questions like this before. So we actually warm up reviewing on part A and B, and then we go specifically to exponentials on C, D, and E. So what we're doing is we're taking a function, a parent function or a starting function, and we are going to convert it into g of x, in this case at the end. And I want to know what transformations do I have to do on the original function to obtain the graph of the end function. So in this case, we're going from plain old x squared to the graph of 4x quantity squared. So what is the first thing that we could do to the graph of x squared to get 4x quantity squared? In other words, what transformation is it when your b value is 4? Horizontal compression. Good. Horizontal compression by a factor of 4. Yeah, it's narrower. Now for a parabola, when you make it narrower, you also make it a little bit steeper. So you could equivalently get the graph of g of x by doing what? Stretching it vertically. So that would be equivalent to a vertical stretch by a factor of, would it be 4 again? No, this is where you have to, would it be 1/4? This is where you actually have to do the math, right? 4x quantity squared is 4x times 4x, which is 4 squared x squared. So it's equivalent to 16 times x squared. So in this case, this is a b value. By expanding it out, you turn it into an a value. So it's equivalent to a vertical stretch by a factor of 16. Yeah, that's review. We've done that already. What's that? What we're doing right now? 4.1. Yeah, we started 4.1 ages ago, seems like. All right, on this one, we're starting with the square root of x, and I want to turn it into the graph of 4 square root of x. So the first thing that we could do is the one that's obvious. This is out in front right now as an a value. That would be a what? Vertical stretch, good, because it's bigger than 1, by a factor of 4, because it's bigger than 1. Now, if you want to look at that, let's do the parent function here. I'll do it kind of in a mustard yellow. Square root of x would look like that. If you vertically stretch it by a factor of 4, 0 is going to stay 0. That one goes up a little bit. That goes up a little bit more. That goes up a little more. That goes up a little bit more. Okay, the bigger the y value, the more it moves. So it ends up looking like that. It also appears that we could obtain that final red graph by doing some equivalent horizontal compression, right? So what would that horizontal compression be? I'll write it out here. A horizontal compression by a factor of, good, 16. Not 2, right? Not 2. You're trying to turn the a value into a b value. So what you have to do in order to get the 4 under the radical is you have to write it as the square root of something. So if you write 4 as the square root of 16, that's a true statement, right? The square root of 16 is 4. Now because they're both under the same square root, you can write both of those under the single square root. And now that turned it into a b value. So that is equivalent to a horizontal compression by a factor of 16. So I might try to bait you like that by putting a nice perfect square out in front of the radical, like a 4 or a 9 or a 16 or a 25, hoping that you'll square root it instead of squaring it. But y'all are too smart for that, so that's just me having fun to no effect. Okay, now we get into the bottom line. And the bottom line deals with the exponential functions that we're dealing with in this section. So we're starting with 3 to the x. Let's go ahead and sketch 3 to the x. 3 to the x in mustard yellow looks something like that. It's exponential growth, passes through the point 0, 1. If I pick that graph up and I move it, what? What does the plus 1 do? Moves it right 1 unit. Yeah, so there it is. I literally just copied it and moved it over 1 unit. It looks like I could achieve that graph a different way. Let's go ahead and write down the first one. We're going to move it right 1 unit. But is there another way to do it? It looks like, would a horizontal compression work? Yeah, what kind of stretch? A vertical stretch? Actually, we're going the other way. We're starting with the mustard yellow graph. So that would have to be some type of vertical compression. Yeah. So it looks like maybe to go from the mustard to the purple, we're going to do a vertical compression by what? Let's go ahead and write that down first. A vertical compression by a factor of, and now we just guess, right? Yeah. As long as you guess correctly, that's fine on a multiple choice. But we're going to go ahead and do it by not guessing. We're going to go ahead and manipulate this. So today we're going to be using a lot of rules of exponents, rules that we reviewed the first week of school. And that was for this reason. So when we get here today, you'd be like, oh yeah, I know how to do that. Right now we have a C value of 1, x minus c. I need to write it, if I'm going to be vertically compressing it, I need to write it as an A value. I need to get from a C value to an A value. So here's what you're going to do. 3 to the quantity x minus 1 is the same as 3 to the x times 3 to the negative first, right? Verify that in your head. We're usually going from this line to that line. Usually, when we are multiplying and the bases are the same, we add the exponents to get this. But it works the other way around as well. If you start with 3 to the x minus 1, you can split it up and say it's 3 to the x times 3 to the negative first. That puts us in the driver's seat now, because what's another name for 3 to the negative first? 1 over 3, which I'm going to write now in the front, because that's a number, 1 over 3 times 3 to the x. That gives us another way to do it. Okay, shifting a right unit now is the same as vertically compressing it by a factor of what? Yeah, 3, not 1/3. So we took it from a C value to an A value. And that's kind of unique for exponentials. All right, any questions or comments on that one? Rules of exponents. Master them, and you'll master logs before you even get to them. All right, here's another one. Now, this one's going to be interesting transformation-wise because it's not immediately obvious. We want to get with from the graph of 3 of x, 3 to the x power, to the graph of 9 to the x power. So let me go ahead and just sketch 3 to the x. It's going to look something like that. And remember, it's not really important to show how steep that is until you sketch another one on the same grid. 9 to the x should be whatter than 3 to the x. Steeper or less steeper? Steeper, okay? Or less steep. I said less steeper. That's double comparative. That's not right. So that would be 9 to the x. It'd be steeper, so faster going to infinity, and then they intersect and cross down here, and it goes to 0 faster. But they both pass to the point 0, 1. All right, so to get to the graph from the purple to the red, would a vertical stretch work or a vertical compression? I have to stretch the purple ones vertically to the right of 0 and compress them to the left of 0 and then not do anything at 0. So a vertical stretch wouldn't work. But could we do something horizontally? Well, I'm starting with the purple, right? So I'd have to take the lavender, really, and bring it in. So that would be a horizontal compression. Yeah. So it's going to be a horizontal compression by a factor of, and then we guess, right? No. Okay, so here's what we're going to do now. It's a little bit more fun. These kind of amp up in their funness level. I want to be able to write 9 to the x in terms of 3 to the x, right? So let's just go ahead and put parentheses where the 9 used to be, and let's see if we can't write 9 as a power of 3. Think hard. Come on. What is 9 as a power of 3? 3 squared. Super duper. So we just wrote 9 as 3 squared. And now again, the rules of exponents. We're raising a power to a power. What do we do with those? We add them or multiply them. This is exponentiation. It comes down one rung to multiplication. We multiply. That becomes 3 to the 2 times x. And there it is. 3 to the 2 times x. Now we know it's going to be a horizontal compression by a factor of 2. Yep, that's it. By a factor of 2. Rules of exponents. That's probably the only way to do that one from the 3 to the x. All right, now the next one. Let's rename that the ending one g of x. I forgot to change that one. So we're starting with 3 to the x, and now we're going to 9 to the x plus first power. All right, so what we're going to do is we're trying to make it steeper from base 3 to base 9, but we also want to shift it left 1 unit ultimately on the graph of 9. So the same thing that we did over here, we're going to do over here. I'm not even going to graph these. Begin with the end in mind. Okay? I want to end up with g of x equals 9 to the x plus first power. If I want to obtain that from the graph of 3 to the x, I need to then write this as something base 3. So let's put a fork in the road because there's two ways to do this. So if we go down the left fork, that would be the same thing we just did. It's something to the x plus first power, and we replace 9 with what? 3 squared. Okay? Now if you multiply, you get 3 to the 2 times, bless you, x plus first power. If you want to distribute and call it 2x plus 2, that's fine, but leaving it like this keeps it in standard transformation form. So the first thing we could do, or the first way to do it, is to take your graph of 3 to the x, and what would the 2 do? Horizontal compression by a factor of 2, then, the sequential word then, followed by left 1 unit. Does it matter the sequence in which you do those? It totally does. On the previous test that we took, some people on the free response described the sequences not from left to right, not in ABCD order, they just did them in random order. If you ever describe a shift, a translation essentially, before any type of dilation, it's going to be wrong. You have to do them in your dear Aunt Sally's order. Okay? Exponentiation, multiplication, division, then addition, subtraction. So that's one way to do it. The other way to do it is to use the rule of exponents that we did over here when we had the x minus 1. I'm going to split 9 to the x plus 1 up as 9 to the x times 9 to the first. That's using the rule of exponents. Now 9 to the first can come in front as an a value. 9 to the first. And then 9 to the x, we'll write it as 3 squared to the x, just like before. And now if I simplify that, we get 9 times 3 to the 2x power. It's equivalent. We're just manipulating an expression. But as it sits right there, that's a separate way to obtain it. The 9 in front now would be a what? An a value. So that's going to be a vertical stretch by a factor of 9, followed by, or then a horizontal compression by a factor of 2. Does the order of those two matter? No, those could be done in either order because they're both multiplication. So really, you can kind of think about it. Everything else, the things that's the same between the two different things is the horizontal compression by a factor of 2. Then you either move it left 1 or you vertically stretch it by a factor of 9. So it's interesting to see that for this function, moving it left, a single unit is equivalent to vertically stretching it by a factor of 9. It makes the graph steeper at that particular value of x. So we could change bases from one to another as long as that base is a relatively nice power of the other one. Okay? I wouldn't ask you to do that with ugly fractional exponents. All right, any questions or comments on that? All right, now we're going to write equations from a graph. I'm going to give you a graph with some information, and you're going to write the equation of the exponential function that represents that graph. Now we're going to start nice and easy, like almost boringly easy. We're going to start with the template of f of x equals b to the x. So in this case, the a value is 1. The y-intercept is 1. So all we have to do is find the base. There's one unknown. We need the base. But because the a is 1, we can assume that the y-intercept is 0, 1. So that passes through the point 0, 1 and the point 2, 25. So how are we going to figure out what the equation is? Well, you're going to substitute in. Look what happens if you substitute the point 0, 1 in up here for f and x. At the point 0, 1, you're going to get 1 equals b to the 0 power. Plug in the 1 for f of x, plug in the 0 for x. What is b to the 0 power? 1. So you get 1 equals 1. True dat. That's fun. We just verified that 1 is 1. So that didn't really help. So we need to use the other point. We're going to do that with the 2 and the 25. That's an x and an f of x that satisfies the equation. So we get 25 equals b to the 2nd power. And now we just need to solve for b. What type of equation is that? Not linear. Not exponential. Replace b with x. It's quadratic. Yeah, that's a quadratic equation. Right? So all you have to do to solve a quadratic equation in this case is undo squaring both sides. How do you undo squaring both sides? Square root both sides, right? And remember, when you take the square root or the 4th root or the 6th root, you have to remember to at least consider what? Plus or minus. So it's either negative square root of 25, which is 5, or positive 5 square root of 5. Do both of them work in this situation? We're trying to find the base of an exponential function. And if you scroll way to the top here in the box, we had certain values b could be. B had to be strictly greater than 1 or strictly between 0 and 1. So it couldn't be 0, it couldn't be 1, and of course it can't be what? Negative. So at least we considered the negative version. But now that we've considered it, we can say, you're not going to work though. So the final equation is f of x equals 5 to the x power. That was pretty easy. Now let me show you another way that we can go about solving this. Taking the square root of both sides certainly works. But the way that you solve polynomial equations is by raising both sides to the reciprocal power. What's the reciprocal of 2? 1/2. And that's the same as taking the square root of both sides. But now it works for any exponent, not even just polynomial functions. It can work for rational functions. We have 2 times 1/2, which is what? 1. So that's why it works. And you have a 25 to the 1/2, which of course is 5 or negative 5. So that's what we're going to do moving forward. Instead of taking the square root of both sides, we'll raise both sides to the reciprocal power. All right, this one here. Go ahead and do this one on your own. Take about a minute. You're starting with the same template, f of x equals b to the x. So you're just trying to find the base. All right, so if you plug in for x and f of x, you get 1/8 equals b cubed. That's a cubic polynomial. So you can either take the cube root of both sides, or you raise both sides to the reciprocal power, which is 1/3. They work the same way. Now, when you take the cube root of something, do you have to consider plus or minus? No, it's only for an even root. If you take the 4th root, square root, 8th root, the 102nd root, then you consider plus or minus. If you take the odd root, then you don't consider plus or minus. It's just whatever the answer is. What is 1/8 to the 1/3 power? 1/2, because it's the cube root of an 8th, right? Which is the cube root of 1 over the cube root of 8. So it's 1 over 2. Once you get the base as 1/2, then all you got to do is plug it back in here. And the good transitional word is so, or 4, therefore, f of x equals, now because you have a base that is a fraction, you want to write it in parentheses. Without the parentheses, it looks like it's just 1 to the x over 2, which is a very different equation. All right, so those are pretty easy, rather boring. Now we're going to notch it up one rung here. Example 10. Write the equation of the exponential functions now of the form f of x equals a times b to the x. So now we're making the allowance that the y-intercept doesn't have to be 1. We're making the allowance for vertical stretches and vertical compressions and reflections across the x-axis. So now we have two things to find. And if you remember from Algebra 2, if there are two unknowns and you're expected to walk away with a single equation, you need how many pieces of information? 2, right? You need as many pieces of info as you have unknowns. Well, we don't have the graph, shuckaroonies, but we do have 2 pieces of information. Great. So we don't even need the graph. So let's go ahead and talk about how we would do this. First of all, I'm going to go ahead and write the model that we're going to use, the template, over again. Notice the point 0, 4 is given. Is that a special point in relation to the graph? That's a very important point. That's the y-intercept, which, remember, that means that that's the initial value. So if you wanted to plug that in right away, you get f of x equals 4 times b to the x. And now it's almost like you don't really have 2 unknowns. You just have 1 unknown, b. Now, if you didn't see that, you should see that. You should pre-think through the problem instead of just jumping in. Here's what you could do. You could plug it in. F of x would be 4 when x is equal to 0. What is b to the 0 power? 1. So 1 times a is a. You get a equals 4. So you can find it that way and then plug it in. And now you're at that point. So you're kind of building this up. Now that we have the a value of 4, we need to find b, which means we need another piece of information. How convenient is that they gave us the second one? So let's go ahead and plug that in now. F of x is 22. F of x is 22. We got 4 now times the base b to the 5th power. So marginally more interesting. This is a 5th degree polynomial equation. We have to solve it by first isolating the variable term, which we have. And now we have to isolate the variable factor, which involves doing what with the 4? Divide both sides by 4. I'm not going to show that. We'll just go straight to the answer on the next line. B to the 5th then is equal to 22/4. Or what? 11/2. That's a better version of it. Now you either take the 5th root of both sides, gross, or raise both sides to the what power? 1/5. Yeah, I'm going to go ahead and write that as a separate line. All right, so the reciprocal of 5 is 1/5. So if I raise both sides to the 1/5 power, do I need to consider plus or minus here? No. If the denominator of your fraction is an odd number, it's like taking the odd root. So we get b to the 5 times the 5th is 1, so that's b to the 1st, equals the 5th root of 11/2. Is 11/2 the perfect 5th root? Is 11 or 2 a perfect 5th root? No. So what you're going to do is you're going to leave your base not as the 5th root of 11/2, but you're going to leave it in rational exponent form. 11/2 to the 1/5 power. That's how you're going to leave it. It doesn't simplify. And now all we have to do to get our final equation is plug it back into there, and we get our final answer. So f of x is equal to 4 times b, which is 11/2 to the 1/5 power, all to the x power. But we're not done just yet. What can we do now since we left the 5th root as a fraction raised to a fraction power? What do you do with those two? You multiply. All right. So your final answer is going to be 4 times the base is 11/2, and now the exponent is 1/5 x, or x/5, x divided by 5, however you want to write it. That is the prettiest version of the answer. The parent function is 11/2, which is exponential what? Growth or decay? Growth, right? The 4 is a vertical stretch by a factor of 4. The 1/5 is a horizontal stretch by a factor of 5. Good. Good. So if it's not a perfect fifth root or third root or whatever, we're going to absorb it in the exponent instead of writing it as the fifth root of 11/2 to the x power. But that would be the same. Let's see how ugly that's going to look. That would be 4 times the fifth root of 11/2 all to the x power. That's just an ugly exponential base. It works. Those two graphs are equivalent. It's just nicer to show the base as a rational number instead of irrational. All right, so that one, I apologize, was a little boring because I gave you the y-intercept. Go ahead and do part B now on your own. Notice you also have the y-intercept. So you're using part A as a model, as a guide to be successful in part B. All right, again, noticing 0, 2 is given. 2 is the y-intercept, so that's the a value. So you can go straight to f of x equals 2 times b to the x. And you've turned a 2 unknown problem into just a 1 unknown. So the correct way to show that you're plugging in is to say at 3 1/2 colon. You're kind of on a free response, kind of narrating your way through the problem to make it easier to follow. 1/2 then equals 2b cubed. If you solve for b cubed by dividing by 2, you don't get a 1. You get half of 2. Or, I'm sorry, half of a half, which is a fourth. It's the same as multiplying both sides by 1/2. Now, 1/4 is not a perfect cube root. If it were, you could just take the cube root of it. Because it's not, we'll just raise it to the 1/3 power on both sides, and we get b equals a fourth to the 1/3. It's an odd root, so you don't need to consider plus or minus. Now, the next step, I put 2 asterisks by. You can really skip that if you want, okay? But I'm plugging it back into that very top line. That's 2 times my base to the x power. Once you do that, if you have a fractional exponent on your base, the next line is always going to be to write it as a product. 1/3 to the x power is the same as to the 1/3 times x power. So if you want to go straight from finding b to your final answer, 1/3 x, that's fine. Okay? But don't skip steps unless you totally understand why and you've mastered the problem, because then you're just inviting careless mistakes into your house. Don't do that. All right, so that ended up being an exponential decay function that was vertically stretched by a factor of 2 and horizontally what by a factor of 3? Stretched. Now, there's something else we could do over here. On this previous one, 11/2 and 4 really had nothing in common, no common factor. But I'm going to do something over here, which will be a segue into the next section. 2 and 1/4 actually do have something in common. They can both be written as powers of 2. So look what else we could do. The fun never ends. for this problem. I'm going to write 1/4 as a power of 2. What is 1/4 as a power of 2? 2 to the negative second power, right? Because 1/4 is 1 over 2 squared. Bring the 2 squared to the top, becomes 2 to the negative second. Now, I can write that as 2 times 2 to the, what's negative 2 times 1/3 x? Negative 2/3 x, right? You multiply. When you raise a power to a power, you multiply. Well, we're not done yet, because now I have my a value as a power of 2, and my base is a power of 2. So I put the 1 there. What can we do with the exponents when we're multiplying and the bases are the same? We add them. So I can write that as negative 2/3 x. Oops, 2 to the power of, sorry, don't forget that. 2 to the negative 2/3 x plus 1th power. And now we can write it exclusively as a power of 2. Might I do that as a multiple choice question? Heck yeah. Fun, 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 fun. All we're doing is we're using the properties of exponents. We spent a lot of time on that at the beginning of the year. So that makes that one a little bit more exciting at the end. But it was rather boring getting the equation because, like on part A, you had the y-intercept. So let's look at example C. I gave you 2 points. Are either one of these the y-intercept? No, how can you tell? There's no 0 for x. Yeah. So this one is exciting. This one's fun. We're going to start with our template, a times b to the x equals f of x. And what you're going to do is you're just going to plug in. Using the first point, you get 10 equals a b to the negative second. And directly underneath there, plug in, you get 1/3 equals a times b to the positive second. What you have done now is you've created a system of equations. And just like in Algebra 2, you're going to solve them simultaneously. In Algebra 2, you probably didn't do exponential systems, but you did polynomial systems, quadratic systems. You can solve them by guess and check, which is not very fast. Substitution, elimination. Elimination is just a specific version of linear combinations. Maybe you used augmented matrices. Maybe you did matrix multiplication. Maybe you even did Cramer's rule. Remember all those? Maybe. The way that you're going to solve an exponential system is going to be pretty easy. So I'm going to call the top equation 1 and the bottom equation 2. Okay? What I'm going to do is I'm going to do equation 1 divided by equation 2. That's legal. Linear combinations works because you are allowed to add, subtract, multiply, or divide one multiple of one equation to a different multiple of the other equation, and you don't change the solutions to the system. So if I take equation 1 divided by equation 2, it's kind of like putting a division bar here and a division bar there. But you don't really want to think of them as division bars. But here's what we'll have on the left. What is 10 divided by 1/3? Stay, change, flip, and you get 30. 10 divided by 1/3 is 30. What happens to the a's on the right side? They divide out. That's awesome. They divide out. So your a divided by a is gone, and you're left with b to the negative 2 divided by b to the positive 2. Now that you're dividing, what do you do with the exponents if the bases are the same? Subtract, right? So negative 2 minus 2 is negative 4. And now all we have to do to solve for b is to raise both sides to the what power? Negative 1/4 power to both sides. Now, 1/4, that's an even root. So we're going to get b to the negative 4 times negative 1/4 is 1, and we get 30 to the negative 1/4. We need to consider plus or minus, but can we have a negative base? No, so we're not even going to write it down. So we end up with 30 to the negative 1/4, or if you like it without a negative exponent, 1/30 to the positive 1/4. That's what you would get if you actually did equation 2 divided by equation 1. It doesn't really matter. They're equivalent. So notice now we found the b first. Now I just got to find the a. So to do that, I'll plug it back into either one of those original equations. Which one is more user-friendly to you, number 1 or number 2? Number 1, okay. So now we're going to plug back into number 1, and we get 10 equals a times b to the negative second. So notice what I did. I put a parenthesis where the b was, and I'm going to plug my 30 to the negative 1/4 in there. And it's just a matter now of solving for a. If I clean up this, what is negative 1/4 times negative 2? Positive 1/2. Is 30 a perfect square root? No, so we'll leave it like that. It's just a number, so now to solve for a, I divide. So I get 10 divided by 30 to the 1/2 power. Or, that's not a very nice version of it. I'm going to write it as 10 times 30 to the what power if I bring it to the top? Negative 1/2. If it's positive 1/2 in the bottom, the exponent on the 30, if I bring it to the top, it's negative 1/2, right? We change the sign. Now that's a nicer version because my base is a power of 30. I want my a to have a power of 30 in it. And so now we're almost done. Now we just say, so f of x is a, which is 10 times 30 to the negative 1/2 power, times b to the x power, which is going to be 30 to the negative 1/4 to the x, which is just negative 1/4 times x. And this is like the gift that keeps on giving. Now because my a and the b have a 30 in them, I can combine those. And I get 10 times 30 to the, when I add the exponents, you get negative 1/4 x minus 1/2. And that's a really nice version of it. Now you can even factor out the negative from both terms in the exponent and say it's 1/30th to the positive 1/4 x plus 1/2. But I'm going to leave it like this. Okay? So that was much more exciting, a lot less boring. But the procedure is the exact same each and every time. Let's finish up with this one here. Negative 5 1/8 and 4 8. We got 5 minutes. If we do it together, we'll have time, and then you can go practice in the worksheet. I would practice these sometime today as soon as you get a chance to reinforce what we're doing. So again, we're starting with our form, f of x equals a times b to the x. Just plugging in, we get 1/8 equals ab to the negative 5th, and we get 8 equals ab to the 4th. If you just want to do the top one divided by the bottom one, you could do that every time. It doesn't matter. Let's do that way. The top one is the 1/8 divided by 8. What's 1/8 divided by 8? 1/64. Okay? The a's are going to divide out now, and you get b to the negative 5 minus 4, which is negative 9th power. If you would have done equation 2 divided by equation 1, you'd have 64 equals b to the positive 9th. That's fine. It's the same thing. Now we raise both sides to the negative 1/9th power, because that's the reciprocal of negative 9, and you get b equals either 1/64th to, yeah? Well, I'm dividing. I'm doing this one divided by that one. So when you're dividing and the bases are the same, you subtract. So it's b to the negative 5 minus 4. Negative 5 minus 4 is negative 9. It's almost, and I don't really want you to show this, but at least temporarily you could put like a division bar like that if you want. That's essentially what we're doing. Now, 1/64 to the negative 1/9 is kind of ugly. This is kind of a win-win. If you flip the fraction, you get 64, and that makes the exponent positive. That's a little bit nicer to use. Now, is 64 a perfect 9th root? No, so we'll just leave it like that. So there's the b value that we're going to use. Now to find a, we just plug it back into either one of those. I'm going to plug it into the second one. Doesn't have fractions, doesn't have negative ones. So we get 8 equals a times b to the 4th. And again, notice how I did that. I just put parentheses to the 4th. Now we drop in the b value, you get 64 to the 1/9. So if you simplify that, you get 64 to the 4/9 power. And now you just got to solve for a. So you get a equals either 8 divided by 64 to the 4/9, Or, if you bring the 64 to the top now, you get 64 to the negative 4/9. And there is the value of A that you're going to use. So now you have your B as a power of 64, and you have your A as a power of 64 factor. So now you're just going to plug it in. So f of x equals A, which is 8 times 64 to the negative 4/9. There's A, times the base, 64, to the 1/9 to the x power is to the 1/9 x power. So again, you can skip that step. Just know that you're going to multiply them. And then the last thing we do, and this will work out this way pretty much every time, you can combine the 64s. So you get 8 times 64 to the 1/9 x minus 4/9 power. And that becomes your new exponent. You're multiplying and the bases are the same, so you're adding the exponents. So on a free response, I would probably give this to you and say, show that the equation is this, or if it were multiple choice, this would be the answer choice that I'd have. Then if you wanted to sketch it, then you could factor out the 1/9 from both terms, put it in standard transformation form, and have more fun yet still to go after this. But we'll stop right there. Practice those. These are the questions that separate the pre-AP from the academic. These types of questions right here, working with all these wonderful exponents. All right, so tomorrow we'll learn about a logistic function. We'll work one problem. You'll use your calculator tomorrow, so if you want to bring it or grab one on your way in tomorrow, we'll finish pretty easily. Maybe answer questions from the worksheet. Worksheets due Wednesday, quiz on Wednesday.